Hello and welcome. We have today another question. Leetcode 1928 minimum cost to reach destination in time. This question has been recently asked by Facebook, so I hope you guys, you know, couldn't can enjoy what I have in store for you. So I'm going to read the question is: there is a country of n cities numbered from 0 to n minus 1, where all the cities are connected by bi-directional roads. The roads are represented by a 2D array edges, xi, yi, time I, denotes a road between cities xi and yi that takes um, time I minutes to travel. Okay, there are multiple roads of different travel times connecting between two cities, but no road connects a city to itself. Okay, cool. So there's no like node that loops to itself. Okay, cool. And each time you pass through a city, you must pay a passing fee. This is represented as a zero index integer array passing fees of length n, where passing fees j is the amount of dollars you pay to pass through city j. Okay, cool. In the beginning, you are at city zero and you want to reach city n minus one in max time, minutes or less. The cost of the journey is a summation of passing fees for each city that you pass through at some point, as a moment of your journey, including the source and destination. So, given max time edges, passing fees return the minimum cost to complete your journey, or minus one if you cannot complete your journey within max time. Okay, cool. So you've been given a graph, right? And you have up to n minus one nodes. So here we have six nodes. So n minus one is what, five. So the last node is five, and you're supposed to start from your zeroth node and then go to n minus one, right? And they're asking you which of the paths would you take, which is going to bear the least cost, right? Provided you can reach in time. So in this case, if you are trying to solve this question and you are trying to, you want to use the greedy method, you want to use Dijkstra's method or Dijkstra's algorithm. In this case, right, Dijkstra's shortest path algorithm, because you do have a single source and a single destination, right? So Dijkstra's single source shortest path algorithm will really work for here. And here in this greedy algorithm, we'll be selecting for the minimum cost, right? Like if two times are the same, let's say this part and this part, right? They all have like maybe they cost 10 minutes to cross, right? But part one has has a cost of one, and this one has a cost of 20, right? Then I will select the one with the cost of 20, right? So that's basically how I'm going to solve it. But that's just algorithm. I think a few other legal questions that might be helpful is to look at the cheapest flight within K-Star's problem. I think that one is also very helpful. But yeah, we will be greedily, selecting the edges, right? So we'll build edges based on the cost also, and then we'll greedily select for the ones with the least cost. So for the first example, right, we'll take this path, right, the path outlined with the red. So we start at so zero, right? The cost of that passing fee is what, five, and then we go from zero to one, right? And the cost is what, one, so it becomes total cost of six, and from one to two, the cost is two. So what becomes eight, and then from eight to five, so from two to five, cost is three. So it becomes a total cost of what, 11, right? And if you add the times for the edges, right, which is 10, 10 here, and 10 here, it is less than 30 minutes, which was the max time. So we would have made it, right? In this case, it becomes 48, right? Because which part are we going to take? We're going to take the part with the red edges again. We start at the source node of 5. We want to get to the node of value 5, right? And then for 5 plus 20 plus 20 here again becomes 45, and plus 5 here again becomes 48. And then the other graph, the last one, in the end, it wasn't able to, whichever part you choose, right? You are not able to build I'm not able to get into the destination before max time. So that's it. So very simple if you know that Shas algorithm. And let's get into the solution. Right? We have and n should be passing fees dot length, right? So the passing fees array gives us the fees. And then I want to build our adjacency list. And then look through and fill every single node with an empty array list initially. All right, so now we look through the edges, right, and build edges. So before I proceed, edges.length key plus plus. Cool. I need to build a class edges and actually change this to edge, right? Because that's the kind of stuff that we want to store in our list. So the adjacent, because we want to store, we want to have a struct which keeps not only the node value, right, but also the cost of the edge, like from 0 to 1. Or the cost will be 10. Sorry, the cost will be 1, and then the time between 0 and 1 is what, 10. So I want to build a class like that. So I have to call the public class edge, excuse me, and then I'll have not just the node value, the time, but also the cost. So I'm just initializing stuff. And basically, this is how we initialize it with classes in Java, basically. Um, cool. So then we come back and now we are looping through the edges, right? So if I have an array, call it edge, right? We have um, edges key, right? And the edge has three different things. It has the source node, right? And mind you, it is bidirectional, right? It has the source node, it has the destination, right? And then it also has what the time it takes, right? So basically, I want to call that T, and then now it's bidirectional, right? So we can go from 0 to 1 and from 1 to 0 again. So I'll say that adjacency list of you, sorry, of you, right? To that, add a new edge, V, right? The edge V, the time, keep the time, and also the cost. So the cost of V is what the passing fees of V, basically. And then I do the reverse for V, right? Right. So after building the graph, essentially, right, what we want to do is to have a distance array, right? So a distance array in this case, normally for Dijkstra one, but in this case would be we are keeping the distance, the times, right? We want to keep count of the times. So the times is what n, right? The least times we've seen for each node. So initially, as with multiple most Dijkstra algorithms, what we want to do is to fill our times or distance array with what's infinity, right? So integer dot max value. That's what we want to fill it with. And then now I want to define our priority queue, right? The priority queue that we'll use, and that will take edge, call it PQ, and that this priority queue is sorted based on the cost of the element, right? So if you have A and B, I want it to sort by what A dot cost minus what B dot cost. Right. So sort according to cost, and then we proceed to add our initial node. So our initial node, we know we are starting at what node 0, right? So it's a new edge, and we start at node 0. What's the cost at being at node? Sorry, what's the time that has been spent so far? It's 0. Right? But what's the cost of being at node 0? It is what it's passing fees 0, right? And I think for the first case, right, the first example, that would be 5 here. Right? So we build an edge, new edge, we add this, and then what I want to do is now go through it with our breadth first search, right? Go through our priority queue with our breadth first search. So the edge, I want to call it current. Let's just pick it up. Right. I'm going to pull the um, latest element, and now that current, I want to keep the node value, right? So I'll call it current node. As equal to current.node. Same for the current time, right? Current.time. And then also what current cost, which is what current.cost. Now, if the path we are on has a current time that is greater than our max time, then we know that, like, we don't want to use this path. So what we want to do is to continue, right? We're going to continue. And if also if we are keeping call it times, right? Times array, and then a current node value. So the current node value is going to correspond to a certain element in the times array. Right now, if that element is less than our current node, right, then what we know is that we've had a shorter, like we've had a quicker time at this point, right? Or we've had a faster path to that point or to that current node. So what we want to do is also what continue. I want to ignore that one, right? So if we ignore them both, what we want to do now is to say that we can downset times of the current node to what current time, right? Because the current time, and then we do the same for its neighbors. So we'll just update and create new edges based on its neighbors, right? So for edge, I'll call the edge neighbor in adjacency list of the current node, right? So its corresponding neighbors. For them, I want to keep what the neighbor node. So let me call it neighbor node, right? Which is neighbor.node. And then also we want to keep neighbors time, and then probably also you probably don't need to keep these variables, right? But I want it so that it looks as clear as possible. So neighbors cost also. So neighbor dot cost. Now we want to update them based on based based on our values for neighbor time and using our values for current time. So what we want to do is to have a variable, I'll call it a new time, where new time is going to be the neighbor's time, right, plus the current time. So if you meet a neighbor, whatever its time is, like basically the edge storing time is, we add current time to it so that the time increases, right? And then the same thing with the cost, right? So new cost is going to be the cost for the neighbor, right? Plus that for the current node that we are looking at, right? And now we want to ask ourselves before we add to our priority queue, right? Is the new time less than or equal to our max time? Right? If it is, then what we want to do is what? To increase what we want to do is to create a new edge having what's the neighbor's node, and then having the new time, right? And then the new cost also. And with that, we add that to the priority queue. And then our priority queue will keep processing and processing and processing. Because we are selecting, right, based on cost, we know for sure that if we do hit the n minus one node, right, we should what? Return the least cost possible. So that's why one thing I want to add here, right? And I'm coming back to this part. But basically an if statement saying that if our current node is equal to what n minus one, then we know that we've hit what our destination, right? We have reached um, we've reached our destination. So if we reach our destination, what do you want to? We just want to return the current cost, right? Because we are interested in the cost, and because we are greedily choosing based on the least cost, right? How our priority queue is, the current cost that we return here is going to be the least possible. So when our while loop terminates, if it does terminate and it doesn't hit, we don't reach the current node, right? Then we want to return what's -1. And that looks good so far. Let me run it. And then it says neighbor. I think neighbor node, right? So that's what I meant. The node value, right? So we pass first three test cases, right? And then let's submit. Oh no, let me add this test case. 1 second. Probably have to pause the video. Oh man. Bugs, time limit exceeded. 1 second. Right, I just saw an issue. Let me adjust this a bit. So the issue or the bug which was causing the TLE is that this condition doesn't even make sense. Basically, I was saying that if the times, right, whatever we have stored in our times array, right, because we want to store at least time it took to get to that kind of now. If that time is less than our current time, right, this is not current on this, our current time. So it's actually even supposed to be less than or equal to, right? Because if we've already reached that time before, it's less than that, then we don't want to, do the process again. So we want to what? Continue. Because this failing was causing me to get TLE issues because that connection is not running. Um to pass for the first four test cases, I added one more. And then we passed for all this like 45%. The top solutions are all like Dijkstra's algorithm. That is, I think, the best way to go about this problem. Really interesting graph problem. I hope you guys, enjoy the video. So the question is going to be like, what's the, runtime? Is the Dijkstra's algorithm. So if you have number of edges, right, there's e log, e log v, right, where v is also the number of vertices. Um, or I like to say like n log n, right? Where we have like n nodes, and then basically like we process each of them in or n edges, right? We process those n edges that we create in our priority queue, right? So that's why I usually go with. Hope you guys enjoyed the video, and I'll see you guys in the next one. Goodbye.